In this video, we're going to talk about something that I mentioned previously, which is how the molecular geometry of a molecule is related to, but slightly different than the electron group geometry. So when our central atom has one or more lone pairs, then the electron group geometry is not going to be the same as the molecular geometry. But it is also important to recognize that the opposite applies, and that is that when our molecule doesn't have any lone pairs, then the electron group geometry is the same as the molecular geometry. So in this table, what I've listed out here is the steric number 2 through 6, and then we have the basic or electron group geometry listed. So for 2 electron groups, it's the linear arrangement. For 3, it's trigonal planar. For 4, it's tetrahedral. For 5, it's trigonal bipyramidal. And for 6, it's octahedral. Then in the subsequent columns, I have what the molecular geometry becomes when we have one of our electron groups being a lone pair, 2 of our electron groups being lone pairs, 3 of our electron groups being lone pairs, or 4 of our electron groups being lone pairs. So if we have steric number 3 and one of our electron groups is a lone pair, the molecular geometry is referred to as bent or angular. If we have a steric number of 4, that is the tetrahedral electron group geometry, and we have one lone pair, then our molecular geometry is referred to as being trigonal bipyramid. And if we have 2 of our electron groups being lone pairs, then our molecular geometry is referred to again as either being bent or angular. So it's important to realize that there is more than one way of arriving at a bent or angular geometry, and so it can be quite important to specify the bond angle to make it clear exactly what you are referring to. When a molecule has steric number equals 5, it'll have the electron group geometry trigonal bipyramidal. If we have one lone pair amongst our electron groups, then we'll end up with what's called the sawhorse or the seesaw arrangement. If we have 2 electron groups that are lone pairs, then we will end up with the T-shaped molecular geometry. And if we have 3 electron groups being lone pairs, then we're all the way back to linear. It gets the most complicated when we have steric number equals 6, which gives us the octahedral electron group geometry. If one of our electron groups is a lone pair, we end up with what's called the square pyramid structure. If 2 of our electron groups are lone pairs, we end up with what's called the square planar structure. If 3 of them are lone pairs, we end up with a T-shaped molecule. And if 4 of them are lone pairs, we're back at linear again. So you can see there's multiple ways of getting bent. There's multiple ways of getting linear. There's a couple of ways of getting T-shaped. So you kind of have to sometimes put in the bond angles to make everything really kind of clear. But that's it. So what you guys need to be aware of is that there's an expectation that you have memorized the material that's in this table, and most importantly that using a table like this of VSEPR geometries, you can, if you have an accurate Lewis diagram, figure out the electron group geometry of a molecule and also its molecular geometry. You have to get the bond angles correct. You have to get the spelling of the names correct. So you really need to know the content of this entire table correctly. So we'll have a look at some molecules now where we have lone pairs on the central atoms. So ozone, when you look at its Lewis structure, you'll see that the central atom has steric number equals 3. So we've got 1, 2, 3 electron groups, and one of them is a lone pair. So because it's got 3 electron groups, the electron group arrangement is trigonal planar, and the ideal angle for trigonal planar is going to be 120 degrees. The molecular geometry for ozone is going to have a different name from the electron group arrangement and is called bent. Sometimes it's also called V-shaped or angular. So the molecular geometry is different from the electron group geometry. Now, something that's kind of interesting about molecules with lone pairs is that lone pairs are held closer to the nucleus of an atom than pairs that are being shared, or what we call bonding pairs. So as a result, lone pairs are more repulsive than bonding pairs of electrons. And so the net result here is that tends to push these guys here, these bonding pairs, a little closer together to one another. And so rather than seeing the perfect bent angle of 120 degrees, the angle in ozone is actually closer to 117 degrees. So we see deviations from ideal bond angles for two reasons. When we have double or triple bonds, those bonds are more repulsive than single bonds, so we get a deviation due to that. And then lone pairs are going to be more repulsive than bonds of any type, and so they tend to cause deviations as well. So yeah, something to keep in mind when you're answering questions about, do you expect to see the ideal bond angle or not? Now let's go to a molecule that has steric number equals 4 and also contains a lone pair. And the classic example of that is ammonia, NH3. So in the Lewis structure of ammonia, we have 3 bonded hydrogen atoms, and then we have 1 lone pair on the nitrogen atom. So it has electron group geometry, tetrahedral, and the bond angle between all of the electron groups would be 100. I'm not very good at drawing these things. 109 degrees. That's going to be the lone pair poking at the top there. Now, when you have the tetrahedral electron group geometry and one of your electron groups is a lone pair, the molecular geometry is referred to as trigonal planar. Now, the ideal steric number for bond angle is 109, or 109.5 to be precise. Now, keeping in mind that a lone pair is extra repulsive, we would expect all of this to kind of get squished together a little bit, kind of moving away from those lone pairs. So this is actually going to ultimately be less than 109.5 because of that lone pair. And sure enough, when you measure it on a real molecule, it's about 108 degrees, so it's coming in a little over 1 less than expected. Okay, so now we're continuing looking at steric number equals 4 molecules, but this time we're going to look at water, and water is interesting because we've got 2 of our electron groups being lone pairs on our central atom. And so when we have a molecule where we've got steric number equals 4, the electron group geometry will be tetrahedral. But because we've got lone pairs, the molecular geometry will have a different name. In this case, we've got 2 lone pairs, so we call it bent or angular. And it's kind of interesting to think about this. The ideal tetrahedral angle is 109.5. Now we've got 2 lone pairs which are extra repulsive, so I'm expecting that to come in quite a lot from 109.5. So what do we see when we measure the bond angle in water? It's a full, 5 degrees under the ideal bond angle, and that's because we've got 2 of these lone pairs here, and that causes a large deviation from the ideal bond angle. All right, so we've looked at 3 electron groups and 4 electron groups closely, where we have 1 or 2 lone pairs. Now we're going to look at molecules that have an expanded valence shell and have 5 electron groups around them. So let's have a look at this. Is the trigonal bipyramidal electron group arrangement. We see this for steric number equals 5. It's interesting because we have 2 types of electron groups. There are these axial ones, and then there are these equatorial ones. And the interesting thing is that the bond angle between the equatorial electron groups is 120, whereas the bond angle between the axial and the equatorial electron groups is 90 degrees. So I'm going to get greater repulsion between axial and equatorial groups than what I am between equatorial groups. So the axial equatorial repulsion is going to be stronger than the equatorial repulsion because the bond angle is less. So as the repulsion between electron groups decreases with increasing a bond angle, there's a variation in the strength of the repulsion between the electron groups in this trigonal bipyramidal geometry. The strongest repulsion will be between equatorial and axial groups because the bond angle there is 90 degrees. Between equatorial groups, where the bond angle is 120 degrees, we're going to have modest repulsion. And the weakest repulsion is between those two that are above and below the equatorial plane, the axial group, so the axial repulsion, because the bond angle between those guys is 180 degrees. So what's going to happen is that electron pairs tend to be arranged in order to reduce the number of equatorial axial repulsions. Okay, so what does that mean for us? Well, it's pretty simple, is that when we add electron groups that are lone pairs, they always go into the equatorial position. So that's pretty much like how this manifests. So when I have a steric number equals 5 molecule with one lone pair, this lone pair goes in the equatorial position. And what I'm left with is my two axial atoms, and then I've got two of my atoms remaining that were from the equatorial group. They've got 120 degrees. Didn't write that very well. 120 degrees between them. Okay. Now, what does it look like kind of in 3 dimensions? It's a little hard to see. The best description of it is what we call seesaw, where we have this linear arrangement around the middle, and then we've got one atom coming towards you, one atom going away from you. These guys would have an ideal bond angle of 120 degrees between them. These guys would have an ideal bond angle of 90 degrees between them. We do have a lone pair there, and that causes everything to get squished up a little bit and move away from that. So we might expect this angle is going to be a bit greater than 90, and this one's going to be a little less than 120. And so when I look at that, what I see is instead of this being 180 between the two axial guys, it's 173. And instead of this being 120 between the two equatorial ones, then it's not, it's 101 degrees. So you get a fairly decent deviation from ideality due to the lone pair. Okay, so when we have steric number equals 5 and we have two lone pairs amongst our electron groups, then we continue in the same idea. Steric number equals 5 is the trigonal bipyramidal electron group geometry. Now we've got two lone pairs, and you can see they are both placed in equatorial positions. And what we end up now is what we call a T-shaped molecule. Okay, so these are your axial electron groups, and this is your last remaining equatorial bond. And it's kind of, all of our bond angles here, in an ideal world, they would be 90 degrees. Now, what we have to do is keep in mind that these guys are extra repulsive, so they kind of push stuff away from them, and so the net result is that these bond angles aren't 90 degrees, they're a little less, closer to 86 degrees. Now, if we had steric number equals 5 and 3 of our electron groups were lone pairs, so say that would be the case, then you can just see that what we're going to end up with is it's going to go in here. It's kind of easy to see on this molecule. It's going to go in there, and we'd be back to a linear arrangement, wouldn't we? All right, okay. So we would end up with like that, and then our lone pairs would be in our trigonal planar arrangement around the middle. But it's kind of tricky to draw. Okay, so I assume that you didn't need a picture for that one. Okay, we're almost there. So now we're going to look at the molecules where we have steric number equals 6, and we're going to look at what happens when you have one lone pair, when you have two lone pairs, etc. 3 lone pairs. Okay, so when you have 6 electron groups around your central atom, the electron group arrangement is called octahedral. And in this configuration, all of the bond angles are 90 degrees. In fact, every position is equivalent. So there's no advantage as to whether we put lone pairs in the axial or in the equatorial position. However, I will say that the convention is when we're drawing these, just for ease of drawing them, is that we tend to add lone pairs in the axial positions first. So when we have a molecule with steric number equals 6 and one lone pair, we're going to put the first lone pair here in the axial position, and what that leaves us with is what we call the square pyramid arrangement. And so the atoms are joined together in such a way that they delineate a square-based pyramid. So this arrangement, the molecular geometry for steric number equals 6 and one lone pair, is referred to as square pyramidal, or sometimes people just say square pyramid. Now, let's think about what the deviations might be here. I guess these guys are going to get kind of pushed up a little bit because we've got this lone pair here. But whenever we've got lone pairs, we normally, unless the effect cancels out, we'll see deviations from the ideal bond angles. But all of these bond angles are 90 degrees, but I think these ones might get compressed a little bit here due to the lone pair. When you have steric number equals 6 with 2 lone pairs, we put the second lone pair also in the axial position, and then that leaves us with 4 attached atoms that are at 90 degrees to one another in the same plane, attached around the middle central atom, and that geometry is referred to as square planar. Now we're going to see 90 degrees between these attached atoms, and the extra repulsion from that lone pair is cancelled out by the extra repulsion from that lone pair, so we don't see any deviation from ideality. A good example of a square planar molecule is xenon tetrafluoride, which is a very rare example of a noble gas forming a stable compound. And Pauling predicted that this compound would form. People thought he was crazy, and it turns out that it's really easy to make, and it's actually kind of like quite a common compound nowadays. So that concludes the section where I contrast molecular geometry with electron group geometry. There'll be one more video in this series which is looking at molecular polarity and how that is different but related to bond polarity.